In a previous section, I gave you an equation, electric field equals omega over 2 sigma naught. I'm going to show you how to actually derive that equation. Now, there are two special versions when we use planes, and that's how we define omega, or the charge density. Now, the first type of charge density we have is charge enclosed per unit area. Now, you know a plane has two sides, which means that if we have the charge enclosed per unit area, that's applying the charge for both sides. But we have another version of omega, and that's for the surface charge density on the conductor's surface. And this is telling us what is the charge density going to be just on one surface, not both surfaces, just on one. We're going to start with condition 1. So in the previous section, where we had the plane with charge uniformly distributed on it, we have positive charges. We're going to draw a unit cylinder. And we're going to draw a unit cylinder on both sides. And we're going to have an electric field leaving both sides of the cylinder. Now we're going to apply the Gauss's law equation. The integral over the surface times the electric field at the point of each area on the surface is equal to the charge enclosed over sigma naught. Now, both of these sections are going to essentially be the same equation, but we're going to have different values for charge enclosed, which is going to lead us to different final equations. So, when we solve this, the electric field at each point on the surface is uniform, so that's a constant. The integral over dA is the surface area of the face, which is equal to 2a. It's equal to 2a because we have two faces, on this side and on this side. And it's equal to the charge enclosed, which we know is omega, charge enclosed per unit area, times the area of the face, over sigma naught. Because the Q enclosed in question here is the part right above the cylinder. So, the density times the area of the cylinder will give us the charge enclosed. Solving for E, simplifying the equation, we get omega over 2 sigma naught, which is the equation we had for the previous plane equation. Now we're going to do condition 2 with the different omega value. First, I'm going to draw the diagram. So we have the surface of a plane with positive charges along it. And we know that this is just the surface. So the plane will continue underneath it. And this represents the plane going on. And we're going to draw the cylinder. And we're going to have an electric field leaving the cylinder and going forward, because there are positive charges. And we're going to do Gauss's law equation. The charge enclosed over sigma naught. So, when we do this, the electric field is constant because at the cylinder's face, the electric field is always the same value, times the surface area. The surface area of the face of the cylinder. It's just area. And in this case, we only have one face. So instead of being 2A, it's just A. In the previous example, it's 2A because we had two different faces for the cylinders. And this is going to be equal to sigma A, the surface charge density on the conductor's surface, which is omega, times the area. Same as before, but with a different omega value, over sigma naught. Sigma naught, we know, is 8.85 times 10 to the negative 12. When we solve for the electric field, we get omega over sigma naught. So two different plane equations for two different versions of omega. And they're going to tell you on your test what type of omega it is. But if you don't know, you're not sure, and you're stuck, it is almost always this one. It is almost always this equation. So if you're stuck, you can't figure it out, use this one. But when you're doing your problem, you think you're going to use one or the other, ask yourself this question: which omega is it?